this program, we'll be covering the different types of switches used in instrumentation applications of control systems. We'll cover the understanding of the devices, their use and application, as well as its troubleshooting. We'll cover position sensing and process control devices. Under position sensing, we'll review limit, proximity, and photoelectric sensors or switches, while under process control, we'll cover pressure, flow, float or level, and temperature sensors, and the operation of solenoid valves.
We'll begin with sensing switches, which, as the name implies, provide information to a circuit by sensing a physical condition. So, let's start by first looking at limit switches.
Limit switches are one of the most common and widely used pilot devices in industrial motor control applications. Their primary objective is to convert mechanical motion into an electrical signal. For example, they are used in applications to limit the travel of a moving part, such as in a drill-to-depth machine, where the workpiece will be drilled until the limit switch is reached. Other applications may include the detection of parts in a conveyor or counting parts in a line. The applications of this pilot device are innumerable. There are many types of limit switches, and depending on the application, the proper type must be selected to obtain the desired control. All of them, however, have the basic operational characteristics. Let's first start by reviewing their construction and the components that form them. Limit switches are composed of basically two parts: the actuator and the electrical contacts. The actuator comprises a lever that provides an actuating mechanism to close the contacts of the switch. In other words, the actuator is the sensing part of the limit switch, which translates the detection into an electrical control signal at the contact assembly, as we'll see shortly.
As we said earlier, limit switches are widely used, mainly because of the actuator options that are available. In fact, a whole program could be dedicated to the application of limit switches and to the selection of one of the many actuators that can be selected. In this program, we provide you with the knowledge necessary so that you can interpret the specifications, installation, and precautions, and also the uses of limit switches.
Actuators come in three basic types, which are the roller arm, plunger, and wobble stick. These actuators are the elements that differentiate one limit switch from another. They are generally mounted on top of the switch body and can be changed without having to completely remove the whole switch. These three types have many different subclassifications, so to speak. Under the roller arm, you have the fixed lever type, the adjustable, and the fork lever type. The roller on top is connected to the arm to provide smooth movement and easy travel and to prevent the mechanism from excessive wear and tear. The design of how the actuator detects a part is the only difference. The plunger actuator requires linear operation for its movement, which can be from the top or from the side. These actuators may also have a top roller in the mechanism, which allows a cam to move past the roller and push into the switch. The plunger actuates the switch assembly by pushing, and care must be taken that the limit switch is not pushed beyond its travel specifications because it could damage the switch mechanism. The wobble lever actuator uses an extended wobble stick to detect movement. The stick can be available in different lengths depending on the application requirements. The length of this actuator allows the switch to be mounted in a safe location where the machine travel will not reach and damage the switch. The contact assembly of a limit switch is available with normally open and normally closed contacts, or a combination of both. This is the section of the pilot device which provides the electrical information to the control circuit. Limit switches are represented by this symbol, regardless of the actuator type being used. The actuator part of the switch can be thought of as being the triangular part of the symbol, which, when actuated, would activate the limit switch contacts. Based on this symbol representation and the type of contacts available, we have the normally open limit switch and the normally closed limit switch. The normally open limit switch closes its contacts when the switch is actuated, while the normally closed limit switch will open its contacts when actuated. In motion detection and control, You'll also find two derivative symbols of the standard normally open and normally closed limit switches. These are the normally open held closed and the normally closed held open limit switches. These symbol representations are essentially the same as the standard normally opened or closed, but for the electrical ladder diagram, they represent a specific condition for the machine. Let's see. The normally open held closed switch indicates that an external force is normally activating the switch without any machine motion, or in other words, the force is always present, just as if a normally open push-button switch were always pushed. When the external force of the switch is removed, the contacts of the switch will open. This would occur if the motion had caused the forcing part away from the switch, thus removing the external force. Likewise, the normally closed held open limit switch operates in the same manner. The normally closed contacts are held open by the external force until it is removed, thus closing the contacts. The limit switch contacts are open or closed accordingly once the actuator has reached a set travel distance. There are several travel specifications which we must be aware of when installing and troubleshooting limit switches to ensure their proper operation. These are pre-travel, over-travel, total travel, and differential travel. In each of these travel positions, the actuator will be making or breaking the limit switch contacts. Let's take a roller-type lever and see the actuation of a normally open limit switch. At the rest position, the lever does not actuate the contacts of the switch. When the lever is traveled to the point of tripping, the contacts will close. This distance, from rest to the start of tripping, is the pre-travel distance, or sometimes called the trip travel. Under normal operation or application of limit switches, the part that was sensed will continue to move in the same direction until the part has passed by. The actuator of the limit switch will continue to move past the pre-travel distance to what is called the over-travel. At this point, the actuator still has the contacts closed. This over-travel movement, allowed by the switch, ensures that the limit switch doesn't break off. The pre-travel plus over-travel distances form the total travel distance of the limit switch. When the part clears the limit switch, the actuator begins to return to its rest position due to the spring action of the switch. The contacts will be back to open at what's called the reset position of the lever actuator. The distance between where the actuator starts to close the contacts for the first time to when it starts to release or reset the contacts back to their normal state is called the differential travel or reset travel. The wobble stick operates in the same manner. In a push type of actuator, like the plunger, the same travel description applies. The contacts after the pre-travel and continue closed during the over-travel. When the action has passed the reset point, the contacts will be back to the normal position. As an electrician or technician, you will be required to install, troubleshoot, and select limit switches in your plant. This will require you to be able to select the best actuator for the application and mount the limit switch in a correct position so that the moving part hits the switch actuator in the right place and that the manufacturer's specifications on hand are followed. Other considerations include the environment or ambient in which the limit switch will be operating and the physical location in the machine. Limit switches should not be installed on surfaces where heat-dissipating elements from the machines are exposed. These include heaters, injection molding machines, or ovens in a foundry. Excessive heat could damage the plastic parts of the rollers or levers and cause the switch to malfunction. To solve this problem, you may use or attach additional extensions to the levers to avoid proximity to a potential problem area within the machine and still provide motion detection of the part. Although limit switches are rugged and meant to last in an industrial environment, you need to be careful so as not to mount limit switches at the lower part of milling machines and lathes where oil and moisture may drop down to the switch and cause corrosion and malfunction. Debris from metal cutting could also cause interference as it builds up between the detecting part and the lever of the limit switch. In these applications, you should look for mounting positions where the amount of cutting oil or coolant liquids dripping on the machine are minimal and be sure that you use watertight or oil-tight limit switches. Extreme vibration, such as that experienced in stamping presses, may cause the limit switch and mountings to become loose and create a malfunction. Here, the solution is to mount the switch in a location where the vibration is minimal or away from the section that creates most of the vibration. The actual wiring and connection of limit switches are very easy and follow the same principles as any other pilot device. Preferably, you should use stranded wire in the connections at the terminal screws in the base of the switch assembly. The actuator, after installation, must be adjusted for proper operation and travel detection of the part in a machine. You also need to make sure that the amount of force or torque required by the limit switch to detect the movement is enough to snap the contacts. If the amount of torque is limited or the machine travel is minimal, you may need to use a precision limit switch. The electrical troubleshooting of limit switches follows the basic methods as those employed to troubleshoot a push button, whether the problem is with an open circuit malfunction of the contacts or a short in the switch due to an overcurrent fault condition. This troubleshooting is done with a voltmeter to check for voltage during contact closures or with power off to check for continuity of the switch contacts. However, if you suspect a limit switch problem, the most important part of troubleshooting it is by duplicating the travel that activates the switch. You have to make sure that you can jog the moving part back and forth across the limit switch so that the contacts can be activated. You would most likely perform this dynamic check after you have tested the operation of the contacts and actuated the limit switch manually without machine movement. When performing dynamic tests, always be aware of electrical and mechanical hazards by exercising extreme caution. If the limit switch is exhibiting intermittent malfunctions, check the speed of the machine travel across the limit switch. If the travel is too fast, the closure of the contacts may not be long enough in duration to allow proper operation. To solve this problem, you may add additional cam length to prolong the contact closure time. Proximity switches are used in a variety of standard and harsh environment applications, requiring the detection or presence of parts without physical contact. Proximity switches are represented by this symbol for a normally open and normally closed configurations. The diamond-like symbol around the standard limit switch representation indicates a solid-state type of switch contact closure. The general operation of the proximity switch is basic. When a part gets close in proximity to the switch will detect it and will open or close its contacts. There are two basic types of proximity switches. One is the inductive type, and the other is the capacitive type. The inductive sensor is designed to detect ferrous-type materials. The inductive proximity switch uses what's known as the eddy current killed oscillator, or ECKO, principle of operation. Basically, this method uses an inductive oscillator to create an RF or radio frequency field out of the end of the sensor. Eddy currents are formed in the metal part and cancel or kill the RF field at the oscillator, which is detected by other switch components, and the contacts are opened or closed. Capacitive proximity switches can be used to detect all materials and are suitable in the detection of fluids and granulars. The capacity switch operates in a similar fashion as the inductive type, except that the oscillating circuit uses one positive and one negative capacitor plates, separated by a poor conductor called a dielectric. When power is applied, a high-frequency field is created similar to that of the inductive switch. Any changes in dielectric field in the outside of the sensor would be detected, and the switch would react by changing states to its contact output. Inductive proximity switches are designed to operate with ferrous metals, mild steel being the perfect setting, while other non-ferrous metals, such as copper, aluminum, and brass, do not fare as well. In fact, aluminum detection distance drops to about 35% of that of mild steel. The capacitive switch is susceptible to ambient conditions such as humidity because of its sensitivity. Some of these capacitive proximity switches, such as the shielded type, can, in turn, create false triggering of the switch. Therefore, under these conditions, care must be exercised during initial installation and adjustments. The bigger the sensor side of the switch, the farther away a detection can be made. The area of the sensor is directly proportional to the distance of detection. These switches are also designed to detect a proper size target at a particular distance. If the target is reduced in size, the switch will detect the target much closer to the sending end. A 25% reduction in target size could mean close to a 50% reduction in sensing distance. Proximity switches must be adjusted to detect a part at a particular distance, and it is advisable that this adjustment be done prior to the actual field wiring. Once the adjustment is done, then the field connections can take place. If there is a problem with the switch detection, it may not necessarily be the contacts or the sensor itself. For example, if the frequency of detection becomes too fast when using an AC proximity switch, you may require a DC switch, which can detect objects at a much faster rate. Also, remember that the size of the part being detected plays a role in the detection.
If you need to troubleshoot the switch for proper operation, make sure that when making electrical checks, you use caution and the proper sensing devices in size and material for which the switch was set. This way you can make sure if the switch is electrically and sensing-wise working okay.
Photoelectric switches are used in applications to detect or sense the presence of a part in a manner similar to proximity switches, except that the photoelectric switch uses a beam of light to detect their presence or absence. These pilot devices can perform this detection at considerable distances without touching the part being detected. Photoelectric devices are also very versatile and rugged and can withstand harsh environments. Photoelectric switches are represented by these symbols for a normally open and a normally closed type switch. Nowadays, there are two basic kinds of photoelectric switches, which are the modulated light source and the fiber optic type. Both of these offer three basic design types, which are the through beam or direct scan, the retroreflective scan, and the diffuse and specular scan, which are used according to the application need. The through beam sends a beam of light to a receiver, which, when broken by a moving part, will trigger a change in the state of the switch. The retroreflective scan sends a scan that is reflected back to the switch. When the beam is broken, the switch is activated. One advantage of this type is that it only requires the wiring of one single unit, while the alignment of the reflector may be non-critical. The diffuse scan reflects a perpendicular beam of light in a diffuse manner off non-shiny or dull surfaces, and is reflected onto a receiver which is set at a predetermined angle, usually 45 degrees, to pick up any diffused reflections. The scanning distances of this type of device are generally limited to no more than 6 inches. The specular scan sends a beam to a shiny surface, which reflects it to a receiver, which is placed at an angle. Note that the positioning of the source and the receiver becomes critical and must be precise. When the beam is broken or reflected, as in this case, then the switch is activated. Fiber optic photoelectric switches are also available using the same type of scan techniques. Fiber optics, though, offer advantages because they can be placed in very tight spaces where detection is required, while its switch base assembly can be mounted elsewhere. In this type of switch, the receiver and emitter controls are located in the same enclosure, with the fiber optic cables, either one or two, going to the detection area. To select the proper photoelectric switch, you must determine the object to be detected, the distance where the source is to be located from the receiver, the response time of the detection, and the ambient of operation. Manufacturers of photoelectric switches can provide you with important application information on the selection of the proper switch. During the installation of the switch, it is important that the sensor and receptacle are mounted in a solid manner to a support bracket to avoid misalignment due to vibration. You can also test after wiring, breaking the beam of light and measuring the voltage at the contacts terminals for proper operation of the contacts and the detection. Most of the problems associated with troubleshooting a photoelectric switch involve the source and reflector not being aligned or being knocked out of alignment. Another problem may be that the target part is not in front of the reflector, or that the part is too small for detection. If the light detection is okay, and the contacts do not activate, you will need to test the contact terminals with a voltmeter to check for voltage. If moisture has gone inside the contact assembly, a corrosion of contacts may have occurred, and the contact assembly would need to be changed. In Part 2, we'll cover the process control sensors used to detect pressure, flow, level, and temperature. Then we'll go over in detail about solenoid-operated valves used in hydraulic, pneumatic, and other liquid flow control applications.